But before we do any specific mechanisms, I want to start by just creating a chart to organize your thoughts for the named reactions. And we said that they all involve enolate nucleophiles. So the identity of the nucleophile is not going to be predictive of what the mechanism is or what the product will look like. Instead, the named reactions are given they're named based on the electrophile that is involved. That's very important to understand. So the electrophile is going to vary. And there are three main named reactions that I want you to be able to list out and think about whether or not there's a leaving group. And then from that discussion, you'll decide what the mechanism is. And particularly, I want you to be able to predict what the product should look like, or the signature functional groups in the product will be closely associated with each named reaction. Starting with the aldol. For the aldol, the electrophile is either an aldehyde or a ketone. So aldehydes and ketones, right? These are electrophiles where the carbonyl carbon has two bonds to oxygen, or is in the +2 oxidation state. They do not have leaving groups, right? You cannot kick out carbon or hydrogen. Those are too strongly basic to ever leave. So if there's no leaving group, then the mechanism is simply addition. There's no elimination that occurs. And after addition, the product of the aldol is always going to be this characteristic functional group, where we have one carbonyl that has an alpha carbon, and that is bound to what was another carbonyl, but is now the beta carbon, or this is a B-hydroxycarbonyl. So for aldol, I want you to think alcohol and carbonyl are in a 1-3 relationship. Okay, the best name for that functional group is a beta-hydroxycarbonyl. So this is the addition product. Because there's no leaving group, we just protonate this O- to make an alcohol. But under certain scenarios, when the reaction is heated, and if there is another alpha proton that's acidic, then we can go on to lose water. Or we can lose H from the alpha carbon, OH from the beta carbon, and this can go through a dehydration after the aldol addition. That dehydration gives the following functional group: an alkene. But specifically, the alkene is between the alpha and the beta position relative to a carbonyl. So this condensation product is known as an alpha-beta unsaturated ketone. And I'll leave it generic. It could be any alpha-beta unsaturated carbonyl. It doesn't have to be a ketone. So overall addition and then condensation, when you lose water, gives the alpha-beta unsaturated or enone compound from the aldol. So let's juxtapose that with the Claisen condensation, where the Claisen condensation now uses some carboxylic acid derivative, where there's a leaving group bound to the carbonyl. Or this carbon is in the +3 oxidation state. Now, 9 times out of 10, the leaving group is an alkoxy group, an ester. But technically, a Claisen type reaction could involve a chloride or something as the leaving group. Because there is a leaving group, The mechanism is addition and then elimination of the leaving group, leading to this product, where the carbonyls are 1,3. So this is a 1,3 dicarbonyl, but you'll see other synonyms for that, such as beta dicarbonyl. One of these carbonyl compounds would have been the enolate with this nucleophilic alpha carbon, and it would have formed a new bond. It could be either bond to the left or to the right of the alpha carbon. We'll see examples of that later. Where the other carbonyl is beta to the first. So this time in the Claisen, because there's a leaving group, it's eliminated and both carbonyls survive. That is fundamentally different from the Aldol, where there's no leaving group and you get an alcohol product. So one more reaction that has a unique electrophile is the Michael addition. And the Michael electrophile is an alpha beta unsaturated carbonyl. Now, don't get confused because the Aldol produces an alpha beta unsaturated carbonyl, but the Michael starts with one. And there's no leaving group involved in the mechanism for the Aldol or Michael. So they're just addition mechanisms. So after addition, the Michael will give you this signature functional group, where you have two carbonyls, but they're much further apart than the Claisen product. Some nucleophilic alpha carbon has attacked an electrophilic beta carbon and made that new bond, but that beta carbon is next to another alpha carbon. So alpha beta alpha linkage means that the carbonyls are at positions 1 and 5 relative to one another. So the signature of the Michael addition is this 1,5 dicarbonyl product. So it's fundamental to be able to take this functional group and name it, and then name the reaction and think back to what the starting materials were, because that's going to be a very important part of synthesis. Towards the end today, we'll talk about another named reaction that's really nothing new, the Robinson annulation. And the Robinson is a Michael addition followed by an intramolecular aldol condensation. So more to come on this, but all of the rules that I wrote out above for Michael and Aldol individually are still true within the Robinson. But the Robinson will always give a product that looks like this. It will be 6-membered ring, always, with an alpha beta double bond conjugated to the carbonyl, which is collectively known as a cyclohexenone.